Hi everyone, my name is Ramil and today I am going to present a recent paper on Explainable AI published by Kirti Divireddy in 2025. The paper is titled A Comparative Study of Explainable AI Methods, Model-Agnostic versus Model-Specific Approach. It looks at four different explanation techniques and compares how they work on image classification tasks. Deep learning models like convolutional neural networks are great at recognizing images and patterns, but they often act like black boxes. That means we don't really know why they made a certain decision. XAI helps open up those black boxes. This is especially important in sensitive areas like healthcare, where doctors must trust AI diagnosis, finance, where fairness matters for loan approvals, autonomous vehicles, where safety is critical, and law, where AI tools must remain transparent and unbiased to ensure justice. Without explanations, AI risks being untrustworthy or even unsafe. The paper focuses on two families of XAI methods. First, model-agnostic methods like Llama and SHAP that work with almost any machine learning model. They don't need to know the internal architecture. Second, model-specific methods like GradCam and guided backpropagation that are designed for deep learning, especially convolutional neural networks. Each family has strengths and weaknesses. Let's start with model-agnostic methods. Llama, or local interpretable model-agnostic explanations, explains a single prediction by creating many slightly altered versions of the input, observing the model's behavior, and then fitting a simpler model like a linear model to approximate what's happening. SHAP, or Shapley additive explanations, is based on cooperative game theory. It assigns each feature a score based on how much it contributes to the final prediction. Unlike Llama, which is more local, SHAP provides both local and global interpretability, but it's also computation expensive. Now the model-specific methods. GradCam, gradient weighted class activation mapping, works by looking at the gradients inside the network and highlights the regions in an image that were most important for a prediction. It produces those heat maps you have probably seen in AI papers, and you can also see one in this slide. Guided backpropagation modifies the way gradients flow backward through the network. It filters out negative signals, so what you see is a high-resolution visualization of the most relevant textures and edges. This makes it especially useful for detailed feature analysis. Here's the experiment the author ran. She used a ResNet 50 model and applied all four methods to classify images of 7 species, including dogs, cats, birds, and even a ladybug. As you can see in this grid, each method tells a slightly different story. Llama and SHAP spread importance more broadly across the body. GradCam zooms in on key discriminative regions like a dog's face or a bird's beak. Guided backpropagation emphasizes edges and fine textures like feather patterns. The same image ends up with 4 different explanations. The results highlight some clear trade-offs. Llama and SHAP are flexible and can work with many models, but they are slower and sometimes less precise. GradCam and guided backpropagation are faster and very detailed, but they only work on convolutional networks. So the main conclusion is there is no one-size-fits-all method. Each has strengths and weaknesses. The best approach is to combine them, a hybrid strategy, to get both broad and precise explanations. This matters in the real world because AI systems are used in high-stakes areas. For example, in healthcare, combining global explanations like SHAP with local detail from GradCam could help doctors to both trust the model and verify the diagnosis. The author argues that the future of XAI is hybrid methods that are not just technically accurate but also scalable and aligned with human intuition. Thank you for listening. This was a quick tour of how different XAI methods compare and why combining them is the most promising path forward.